So our delta is going to be in terms of epsilon. So in effect, it's like it's going to be a formula. So we're going to say, delta might be equal to epsilon over 5 or epsilon over 3 or something. So whatever you chose for epsilon, that's a prescription for what you would do to find delta. And so we are finding then delta for every or any epsilon that you could choose. And that's what we mean by the limit existing. Now, I'm going to ask you to do this on a test, but you will never see a problem having to do with epsilon and delta on the AP exam. And it's not going to be something that is going to impact your success in this class and understanding. But wrestle with it a bit, because I think there's value in that. And for some people, it may help kind of clarify what we mean by a limit and how precise that really is, I hope. Maybe not. So what we're going to do, we're always going to start with this, and we're going to end with that. So we need to know what is this and what is our target. So our f of x is the x squared, and our limit, the L, is at 9. And our epsilon is going to be just the symbol epsilon. You okay with that? And our goal, what we want to get to, is going to be x minus, well, what's the c? It's that 3. And what we're going to get, remember this is not going to be a nice number, but it's going to be something with an epsilon in it. Okay? So we start here and I don't know where to go, so but the only thing that comes to mind is maybe factor that thing. And so we will. And so we'll factor that into x minus 3, x plus 3 is less than epsilon. Now this is good news because we want an x minus 3 at the end of the day. We don't want the x plus 3. So we can split this up into their own absolute values. So remember, it's a fact that the absolute value of a times b is the absolute value of a times the absolute value of b. So we can split these into their own absolute values. And we want to keep the x minus 3, but we want to get rid of the x plus 3. Now before, when that was an ordinary number, we could divide it to the other side. When it's a variable, that's not a legal move because we don't know that x isn't equal to 0, that x plus 3 isn't equal to 0. So for the wrong choice of x, dividing by this would be undefined. So this is where we use a little bit of kind of artistic license. Since we're only really interested in the values of x that are close to 3. We have the freedom to say, what do we mean by close to 3? And you just have to communicate that. So I would say, and for our purposes, close to 3 for the problems we do can be within 1 on either side. So we could think of close to 3 as being between 2 and 4. So you just have to communicate that. So we're going to say for 2 less than x less than 4, the absolute value of x plus 3 will be less than, and now you have to figure out what's the biggest the absolute value of x plus 3 could be when x goes from 2 to 4.
7.
It'd be 7, right? It's going to be when x is 4. So when x is 2, we can get 5. And 3 is going to take us up to 6. 4 is going to take us all the way to 7. So that is going to be less than 7. So since we're only going to look at x on this interval now our inequality, you can build a chain of inequalities. So the absolute value of x minus 3 times the absolute value of x plus 3 is going to be less than, and I can replace this by 7. Since that is less than 7, this product is going to be less than that product, which we're trying to make less than epsilon. So now I can put that in my rearview mirror and just look at this. And now that I've replaced that thing with a variable that was a little iffy, by something with an ordinary number, now I'm free to divide that over. And so we could get x minus 3 is less than epsilon over 7. That is our delta. So this is a true proof because our definition of a limit, that Cauchy definition, says for any value of epsilon, we can find the value of delta. Well, here's our prescription, our formula. You pick whatever epsilon you want, 0.1, 0.001, 0.0000001, that's fine, I come up with a delta. So I've shown that we can find a delta no matter how small you make epsilon. Therefore, the limit exists and is equal to none. That make sense? It's really pretty abstract. So it's a little unnerving because you have to do this, kind of leap here and say, okay, here's what we're going to do. As long as you communicate, that's okay. Now, is that the only thing that would work? No, it's a value of delta for any value of epsilon, and that's all we need to do. Okay? Let me change gears. On the back of that limits worksheet, there was a crazy problem with all kinds of limits, and you were supposed to come up with a graph of a function that satisfied all those limits. So I'm going to do one like that. Okay, I'm going to make one up, and actually I have one made up. And I'll walk you through kind of how that works. And you can see another one if you look at the supplemental videos. And you should also do the one on that worksheet. There we go. So we are going to graph a function that satisfies the following limits. And there will be a few of them. So the limit as x goes to infinity of f of x is equal to 3. The limit as x goes to negative infinity of f of x is negative 2. The limit as x approaches negative 1 from the left of f of x equals infinity. The limit as x approaches negative 1 from the right of f of x is negative infinity. The limit as x approaches 2 from the left is negative 1. Is positive 1. The limit as x approaches 2 from the right of f of x is negative 1, and f of 2 is equal to 0. And let's say the limit as x approaches 4 of f of x is equal to 5, and f of 4 is undefined. So with these minor restrictions, you can come up with a graph. I'm going to give myself room to make the graph. So as you're writing this down, what I'm going to do first is go through and kind of make notes on the graph about features that it has to have, how we're going to accommodate all these limits. Then I'm going to come back and go from left to right and actually draw the graph. But first I'm just going to try to make notations about how we can come up with something that's going to do all these limits. I'm waiting for people to get caught up because I want you to be able to think and digest. You ready? Priya, you ready? You ready to go on? Okay, so I'm going to start with these here. So limit as x goes to infinity of is equal to 3 means we have a horizontal asymptote to the right of 3. So I'm going to put that down over here. That's a note that we're going to have to, way out there, approach that horizontal line. The limit as x goes to negative infinity is -2. So I'm going to go to -2, and I'm going to put a horizontal asymptote to the left at -2. So clearly this is not a rational function because we have different asymptotes in different directions. That could never have happened in the problems we talked about in AP Prep last year. Now, as we approach -1 from the left, it goes to infinity. So that means we're going to get a vertical asymptote at -1. So I'm going to go, there's -1. And I'm going to put in a vertical asymptote. I'll label that -1. And on the left side, I'm going to show that we're going to go to positive infinity by putting just a little arrow up here on the left side. So I can come back when I graph this and know I've got to go up there. So as I come to that asymptote, I'm going to have to either go up or down. That's going to tell me to go up. On the other side, as we approach -1 from the right, we're going to go to negative infinity. So I'm going to, down here, put a little arrow so I know that as I come in this way, we're going to have to dive down. Limit as x goes to 2 from the left is 1. So I'm going to go to 2, 1, 2. It wants to be a y value of 1. So I don't know yet if that's defined or not. So at this point in time, I'm going to make it an open circle. That may change when I get more information. And this is approaching from the left. So I'm just going to put a little tail on this thing on the left side. So when I come back to graph this, I know that we're going to come in this way from, I don't know which way we're going to come yet, from the left, but maybe not from the right. And in fact, from the right, we're going to be at -1. So I'm going to come down here, put an open circle there, and put a tail there on the right side, because as we come in from the right, we're going to approach that y value of -1. And the actual value of the function is going to be 0. So I'm going to graph this in purple. So that's a point that I actually know is going to be 2, 0. Is going to be right there. The rest of it is just guidelines at this point. Is that okay? Okay, probably okay? Okay, then here we're going to approach 4. The limit as x goes to 4 is 5. And this doesn't have a one-sided limit, which means it must be a two-sided limit. So it wants to, when x is 4, be a y value of 5. So I'm going to go 1, 2, 3, 4, 1, 2, 3, 4, 5. I'll go there and I'm going to put an open circle because I don't know yet if that's defined or not. And I'm going to put tails on both sides because we're going to approach that as a two-sided limit because it wasn't given the direction in the upper right-hand corner of 4. And in fact, it's undefined, which means I'm going to leave it blank. Okay, so I got all the notations there. Now I'm going to go back to the far left and I'm going to try to connect this. I know out here it's got to approach -2. As I scan from left to right, the next thing I see is it's got to go to positive infinity up here. So I have to draw something that's going to go up there and then come up there. So, I mean, the boring way to do it, which is fine because boring is still correct, would be there. Those that feel more creative and feel this is too restrictive, you can remember that as you approach this asymptote, doesn't mean it has to stay above. You could, if you like, be daring and make it get below and approach that asymptote from below. Or, for those that are really, really creative, you could say, I feel the expression is going to cross there an infinite number of times, but continue to get closer and closer to that asymptote. As long as those kind of loops get smaller and smaller as you go out there, that still qualifies as an asymptote. The choices are virtually limitless, which doesn't mean that everything is correct. Now we're going to skip over here. Now we pick it up down here. And as we go left to right, the next thing we see is it's got to approach this from the left. So I'm going to go like that. Then it's defined there. We already got that. Then down here we see it comes from the right. So I'm going to pick it up here. And the next thing I see is got to approach this from the left. Whew, not much room to get up there. There's got to be a function, right? So don't draw anything that's going to fail the vertical line test. Then we're going to go from here to there. Well, I'm only feeling mildly creative, so I'm going to make an approach from below, but as long as it's getting closer and closer to that asymptote. That's one possible correction, solution. There's actually a few. Okay, so you should definitely try. I got a feeling this is going to show up on a test. Just have a hunch. So do the practice one that's on the back of that worksheet, and also there's another one on that supplemental review, and we can do others if you want to use for after school. Okay, questions so far? Okay, so any burning question from the homework? I can't do a lot, but I can do maybe an example if you like. And the one that started 21, I think it is brutally tough.
Yeah, can we do that one?
It's in there's a supplemental video that'll walk you through it.
Oh.
Because that will take an extended amount of time.
Okay.
So I'm gonna kind of guard the time so we can get through today's lesson. If that doesn't make sense, come see me and I'll go through it with you.
Okay.
But I think I've gone through that in some detail because it's crazy hard. The starred ones mean they're very long and very difficult. So that's just kind of the warning, because sometimes you can do a problem and you think it's really hard and difficult just because you didn't understand it and it's not really that long. Or other times you think, that's nothing. And if it's starred, I'm telling you, no, it really is long and difficult. So if that's the way you're interpreting it, you might be interpreting it right. And if you think that's a 5-second question, you didn't understand the question and you need to put some more thought into it. Anything other than that one?
I looked at 27.
Do you know what that is?
Limit of x plus 3, and then as x approaches 2.
And this, I think, if I remember right, they didn't give you a value for epsilon. Okay, so this is a true proof. So we're going to start with, as we always do, and you don't have to memorize this because I'll give that to you on the test. And our goal is to get to this. And in this case, the delta is going to have epsilon in it. So let's see what we know. The f of x is going to be the x plus 3. And the L, well, they didn't tell us the L. We're going to talk about this today. So we're going to talk about today what we call direct substitution. And we'll just plug the limit value, the thing that it approaches, in for x, 2 plus 3. And that's going to be our limit, our capital L, 5. As long as everything goes well, that's going to work. And we'll look at places where it doesn't go well and try to come up with options for what we do then. And we're trying to get to, this is the C. So we're trying to get to x minus 2. So this one isn't really all that exciting because we're there. And so what that's saying is that the delta is the epsilon. And so what's happening is because this is a straight line and its slope is 2, then if we want to be within 0.5 of the limit point, we're going to choose x values that are within 0.5 of the C. If If we want to be within 0.2 of whatever capital L is, we're going to go choose x as within 0.2 because we're just doing that rise and run. If this was linear and say 2, then this would be epsilon over 2. And if this was a slope of 5, we get epsilon over 5. And it gets way more complicated when this is not linear, like we saw on the example that we started class with. Okay? Okay, so let's dive into some new stuff. We're going to talk about finding limits analytically. So let's pause a moment and think about how we got to where we are. So we started by talking about trying to get an understanding of what it means for a limit to exist. And we said the limit talks about what happens to a function close to x equals c, but what actually happens at c makes no difference in terms of the limit. We said if as x gets closer and closer to c, the y values get closer and closer to a single number L, then our limit as x approaches c is equal to L. The function may be undefined there or defined to be something else, that doesn't matter. We said there are 3 ways that a limit can fail to exist. One is, good. So it could be a vertical asymptote, which we say means it could be infinite. It could be same infinity or different infinities, or infinity on one side and just nothing solid on the other, and the limit doesn't exist. Second way the limit can fail to exist, that weird oscillation thing like we saw with sine of 1 over x. Because it's oscillating wildly, it's not getting closer and closer to a single value, but it's bouncing around and getting a whole bunch of y values no matter how close we get to the limit point. And the third way is?
It's different as it approaches from the left and the right.
So we say left-hand limit different than right-hand limit. Okay, so left-hand limit different than right-hand limit, could be infinite, or it could oscillate. Those are the 3 ways the limit can fail to exist. Now, then we talked about epsilon delta, which is this crazy mathematical definition, which is really weird and challenging and very abstract and confusing, but we'll fight our way through it. Now, what we're going to learn is some analytical or algebraic ways to determine what a limit is. So the first one we actually started doing in the stuff we did last time. It was called direct substitution. And this is always where we want to start. So if we take, say, the limit as x approaches, say, 5 of 1 over x minus 2. So the way we always start a limit is we take what we're approaching, that value of x, and just plug it into the function. And if that turns out to be a number, that's it. That's the limit. We call that direct substitution. So if we plug in the 5, we get 1/3. There it is. That's the limit. Because this worked, then our function is behaving very nicely around that limit point, and there's no big issue. So then the issue comes, well, what if it doesn't behave nicely? And now we got to think a little bit, and we're going to have some different options. So one might be the limit as x approaches 2 of, say, 1 over x minus 2. Now here's where things get kind of weird. Now if we plug 2 in there directly, we get 1 divided by 0, but 1 divided by 0 is not defined. But that's okay, we just have to interpret. Remember, we don't care what happens at the point, but as x gets really close to 2, x minus 2 is getting close to 0. So you're getting 1 divided by a very, very small number, which means this is doing what? It's getting really big. Okay, so it's going to infinity. Now, it could be, if you're plugging in numbers that are a little bit less than 2, then it's going to be going to negative infinity. because you're going to be putting in something like 1.9, 1.99, 1.999, and you're getting 1 over, say, a negative 1/1000th, which is going to be negative 1,000. It's taken off there. But if you're coming in from the right side, like 2.0001, you're dividing by a very small positive number, and it's going to positive infinity. But either way, if this is 0 when we direct substitute it in, this is blowing up. It might be blowing up positive, it might be blowing up negative, it might be doing 1 on one side and 1 on the other. It's all the same to us. The limit does not exist. Not because it's 0 at that point, because we don't care what happens there, but because as we get close to x equals 2, the denominator is very, very small, which means the y values are getting very, very large, or going large without bound. Okay? If we do the limit as x approaches 2 of x minus 2 over x plus 1, we'll direct substitute in. And we'll get 0 on top and 3 on the bottom. How do you interpret that? Well, that's just 0, right? And 0 is a perfectly good number. That's our limit. So that's not an issue if you get 0 on top. It's the 0 on the bottom. Okay? Question?
So in the case where it's 1 over 0, will it always be does not exist?
Yes. And this is the safer option because it's always true. You know, if this was, so if you said 1 over x minus 2 and it was a two-sided limit, and you said that was infinity, that would be wrong. Because it's going to be positive infinity on one side and negative infinity on the other. If this was x minus 2 squared, then no matter which side you come from, the squaring is going to make it positive. And you said this, that would be considered correct. So if you're going to say infinity, you have to be very thoughtful and make sure that it really is going to the same infinity, or it would be wrong. But this is always correct. So this is, I think, the safer answer. Because regardless of which infinity or either infinity it goes to, it's not going to exist. Okay, now here's where it gets more interesting. So we were doing that last time without calling it direct substitution on that homework, some of the ones that you did on your epsilon delta. Now, second one is going to be the way out of it is to factor. So suppose we take the limit as x approaches, particular one in range. We can say as x approaches 2 of x squared minus 4 over x minus 2. So again, we always start by plugging in, by direct substituting in that value of c in for x. And so when you do that, you got to be careful about equal signs with limits. So I'm going to use an arrow, it's a little safer. It's going to be 2 squared minus 4 over 2 minus 2. That's going to be 4 minus 4 over 2 minus 2. So you get 0 over 0. Now this is not following any rules. So if you get to, now we talked about in the earlier example, 0 over a non-zero is 0. A non-zero over 0 means it's going to not exist because it's going to be infinite. This, we say, is indeterminate. By indeterminate, we mean we don't know. We cannot determine, just looking at 0 over 0, if the limit exists or not. And if the limit does exist, what is it equal to? So what this is telling us is we have to do some work. We have to do something clever to resolve this and see what really is happening. And so one thing we can do is to factor. And so the way to do this is to say, well, we're going to factor that x squared minus 4 into x minus 2x plus 2. Now we can cancel those x minus 2's. And that's where the 0 over 0 is coming from that part of it. So now what we get is the limit as x approaches 2 of x plus 2. Now we can direct substitute in. And 2 plus 2 is going to be 4. That's our limit. Okay? So that's the algebra, the mechanics of it. So big picture, what's happening here? When we cancel this, what's that telling us about the graph? There's a hole in the graph, right? But after we resolve that hole in the graph thing, we just had a straight line. So we are taking the limit as x approaches 2 of this line. It's getting closer and closer to y value 4, but right there, it's actually undefined. But that doesn't matter in terms of the limit. We're good to go. You don't have to know the picture, but it's kind of nice to know that. Okay, so that's the second option, is the fact. Now, I'll show you one that's kind of tricky because this will come up on your homework, something like this. So, question? So the limit as x approaches 1 of x cubed minus 1 over x minus 1. So we direct substitute in, and we get 1 minus 1, 0, 1 minus 1. 0 over 0 is indeterminate. So we're going to try to factor it. Wow, that is the problem. At one time, we talked about how to factor the difference of 2 cubes. Do you remember? I do. I taught it in this very room. You were all present for that. But the problem is you forget, right? So that's okay. We have too many things that we're going to have to memorize. Derivatives, integrals, all this kind of stuff. Your mind is going to be full of things that you have to memorize and hang on to. This is not that important. But we had another thing we learned that will help us here. If we plug in 1 and it makes that equal to 0, what must be true? What do we know is a factor of x cubed minus 1? X minus 1. If 1 makes it a 0, x minus that number is a factor. Well, you may or may not remember how to synthetically divide, but we can all long divide. And so we can get there this way. And so this is something like a long-term learning that you can know today and still know May 4th. Okay, should it come up. Whereas if I tell you how to factor the difference of 2 cubes today, and we don't do another problem until May 4th, it's gone. You prove that over this summer, right? Okay, but so this is long term. So I'm going to go 0x squared, 0x, and minus 1, just to fill in placeholders. Remember doing this? Oh, come on, we did it. What times x is x cubed?
X squared.
X squared. X squared times x is x to the third. X squared times negative 1 is negative x squared. And division of polynomials is something you're going to have to be able to do. This will come up in other contexts as well. So knowing the factorization of the difference of 2 cubes, that's not critical. Long dividing polynomials, that's critical. You got to know that. We're subtracting this. That's gone. 0 minus the negative makes that x squared. 0x minus 1. We do it again. What times x is x squared?
X. Negative. Isn't it a negative x?
But we want a minus negative.
Oh, yeah.
Okay, so remember we're subtracting that. Okay, so we go with an x. So x squared minus x, and remember we're going to subtract that quantity. So the x squared minus x squared drops out. 0 minus negative x is x, bring down to minus 1. What times x is x? 1. And 1 times x minus 1 is x minus 1. And we knew it was going to come out even because 1 made that 0, so x minus 1 had to divide in there evenly. Well, there's your factorization. So we are going to go to x minus 1 times x squared plus x plus 1 all over that x minus 1. Okay, there's our x cubed minus 1, and there's the denominator. We can now cancel the culprit, that thing that was making that be 0 over 0, and we're going to get x squared plus x plus 1. Now, take that limit as x approaches 1, and it's going to be 3. Make sense? Okay. So, direct substitution, factor, and cancel. Then direct substitute. third is going to be rationalized. And that may be rationalize a numerator or a denominator. We'll see. So, suppose we have the limit as x approaches 0 of the square root of x plus 4 minus 2 all over x. Square root of x plus 4 minus 2 all over x. So we start always direct substitute in. We put in 0. 0 plus 4 is 4. Square root of 4 is 2. 2 minus 2 is 0. 0 on the bottom. Uh-oh, there's our dreaded 0 over 0 indeterminate. I don't know how to factor square root of x plus 4 minus 2, so that's not an option. Here is our next option. We're going to multiply top and bottom by the conjugate of wherever that radical is. It might be numerator, it might be denominator. So we're going to, in this case, rationalize the numerator. We're going to multiply by the square root of x plus 4 plus 2. And we'll do that top and bottom. So we're multiplying by 1 in a nice form, a form that's going to help us. So now we have a minus b times a plus b. That's going to become a squared minus b squared. So we're going to get the limit as x goes to 0. Squaring the x plus 4, the square root of x plus 4 is going to just remove the radical. The negative 2 times 2 is going to be a minus 4. And let's just leave it factored in the denominator because I got a good feeling that this x is going to cancel in due time. So here we are. Okay? So the 4 and the negative 4 kill each other off once they're out of the picture. Now we're free to cancel the x's. And so we're going to get that limit as x goes to 0 of 1 over the square root of x plus 4 plus 2. You with me? Now we can let direct substitute in the 0 for the x. Square root of 4 is 2, plus 2 is 4. Our limit is going to be 1/4. Now, occasionally you will get something that you just can't find a clever solution to. So I'm going to put it as a technique, but it's mostly a technique of last resort. So I'm going to say plug in numbers close to C. That is really close to C. So I don't know if you can recognize what's going to happen here. Suppose I say the limit as x goes to 3, and we'd say x minus 3 over the absolute value of x minus 3. Now, you may remember what the graph of this looks like. I hope so. If so, then you don't have to do what I'm going to do here. You can know what that graph is. But if you don't, there's not a great technique for this. You can't factor it. You can't rationalize it. There's no good way around it, but you got to come up with an answer. So sometimes what you can do is, let's look at what happens when you let x be 3.1 and you let, say, x be 2.9. And see if that's getting close to some number. And then see if we can figure out if the limit exists or not. And if it does exist, what that number is. So, for example, you put in 3.1, and this is going to lead to 3.1 minus 3 is 0.1. And 3.1 minus 3 is 0.1, and the absolute value is still 0.1, which is anything divided by itself is 1. Is that okay? Now, if we do the 2.9, we've got 2.9 minus 3 is negative 0.1. And 2.9 minus 3 is negative 0.1, but the absolute value becomes positive 0.1. So something divided by itself, but one's negative, one's positive, is going to be, so does it look like they're getting closer and closer to the same thing? They are not. So this is, if you remember, we did absolute value of x over x. This is just a translation of that. And so this in fact means the limit does not exist. It's not getting closer and closer to a single number. If you remember the graph, this is just translated over 3. And so what you're getting is that to the right, we're going to get that these are the same sign. And to the left, they're the opposite sign. So you're getting this place where on one side it's approaching 1 from the right, the other it's approaching -1. Since the right-hand limit is different than the left-hand limit, the limit doesn't exist. Okay? Okay. So let's talk about limits as x goes to a positive or negative infinity. Now we did some of this last year in AP Prep with rational functions. So I'm going to refresh your memory here. I'm going to put 3 examples up, and we'll talk about what our strategy is and how we can determine what that limit is. So if we have, say, a limit as x goes to infinity of, say, 2x plus 3 over x minus 2. That's our first example. The limit as x goes to infinity of x squared plus 3 over 5 minus x. That's our second example. And the limit as x goes to infinity of x plus 1 over 1 minus x squared. There's our third example. Do you remember what our strategy is for this? Because we did this when we were looking for horizontal asymptotes, is the context that this came up with.
Plug in something really, really big, like mentally.
Yeah, well, it does. So what happens is x is really, really big, 1,000, a million, a billion. This is getting huge. 2 times a million is huge, and this little old plus 3, it's like, who even notices it? A million minus 2, that minus 2 is like a gnat. We ignore that, right? So this is going to act like the highest powers of x and their coefficients. And that's the kind of the shortcut way of doing this. So that's going to act like 2x over x, which we know is going to be 2. That is our limit. Does that make sense how we did that? So and we use that strategy in the others as well. As x gets really, really big, x squared gets huge, this x is getting big, the 3 and the 5, they're insignificant. So we overlook the others and just focus on the highest powers of x and their coefficients. So this is going to act like x squared over negative x. But now, that's going to act like x over -1. As x gets huge, what's this approaching? So you could say, correctly, negative infinity, or what's our safe bet? Does not exist. It is not getting closer and closer to a single number. You okay with that? Same strategy on the next one. We focus on the highest powers of x and their coefficients. The other stuff is insignificant. So this is going to start acting like x over negative x squared. We can think of that as canceling, and it's going to act like 1 over negative x, or -1 over x. As x gets huge, 1,000, million, billion, this is getting really close to 0, which is the same as -0, right? Okay. All right. Well, that was a review of old stuff. Let's talk about new stuff. So let's talk about the limit as x goes to infinity. I'm going to put 2 of them up here. Limit as x goes to infinity of the square root of x squared plus 3 over x. And then we will compare and contrast that to the limit as x goes to negative infinity of the square root of x squared plus 3 over x. So same expressions. One's going to positive infinity, one's going to negative infinity. Now last year, when all we did was rational functions, I said with a rational function, polynomial or polynomial, the limit as x goes to infinity is always the same as x going to negative infinity. So there's no need to do them both. With a radical, this is not a rational function any longer. So now these may or may not be the same. We can't assume that. Okay, here's our reasoning. You ready? As x gets really, really big, this plus 3 gets dominated. It's insignificant. It's almost invisible. So this is going to act like the square root of x squared over x. Now is where you got to be careful. Think before you respond. The square root of x squared is equal to not x. What? Not positive or negative x. This symbol means non-negative. So this square root of anything could never be a negative number. Is the square root of x squared equal to x? Is this equal to negative 5? Can't be. Oh, it has to be positive. There's 2 square roots of 25, 5 and negative 5. This symbol means take the non-negative one. So what we get here is not x squared because x might be a negative number, but a square root of anything cannot be negative. Therefore, it must be the absolute value of x. Life gets always more complicated. Well, it's no big deal. We're going to positive infinities. Positive, absolute value of positive is still positive. What's this going to go to? 1, right? No matter what you plug in, absolute value of 1,000 over 1,000 is 1. Absolute value of 1,000,000 over 1,000,000 is 1. Mr. Street's just paranoid. All right. Now we're going to negative infinity. Same story, right? It's going to go to, it's going to act like square root of x squared over x. But you hear Mr. Street's paranoid voice in your head. No, that's not true. I wish you would hear my voice in your head. Can't get in there, but I'll keep trying. So as x goes to negative infinity, what does this go to? Negative. Oh, crazy, crazy, crazy. Let's talk about a piecewise function in the 2 minutes we have left. Oh, you thought you were done with these. You're never done with those. That's a recurring nightmare. So let's look at f of x is equal to, we'll say x plus 2 for x less than 5 and 15 minus 2x for x greater than or equal to 5. And of course, the only interesting question to ask in terms of limits is, what is the limit as x approaches 5? Lots of questions we could ask, but it won't be very interesting. Okay, well, for a limit to exist, the left-hand limit must be equal to the right-hand limit. So we can say the left-hand limit, as we approach using numbers less than 5, which track are we on, top or bottom? If we're using numbers less than 5, top. Is that what you said? Okay, you were right. Then that's going to be 5 plus 2 is equal to 7. Is that okay? Right-hand limit, and as we plug in numbers that are bigger than 5, puts us on top or bottom. So we're going to go 15 minus 2 times 5, that's 15 minus 10, that's going to be 5. Left-hand limit is not equal to the right-hand limit. Therefore, our limit
Would you
is...
come to the counseling office? Jesse Prater?
Oh, good day today, guys. That was good.